Hello everyone. Uh, in this class, we will be discussing week 2 of the course unit operations of particulate matter. And the unit 2 content was basically around the various juggleries and the concepts related to filtration operation. And this filtration operation uh, is discussed in the detail in the week 2. And then this various filtration, basically batch filtration and the continuous filtration has been discussed thoroughly along with some examples and its types. In that, lots of different classifications of the filtration unit has been done. So let me just make it green. Yes, now it is okay. So in the present lecture, we will be going to solve these 15 questions, and I will be taking some more questions, some more numerical problem, which will be anyway beneficial to you in terms of getting your concepts and good hand on the numerical aspect, and as well as some of the basic conceptual questions that will be anyway somewhere around the slides from the course. So this particular lecture will be covering that, and meanwhile I will be solving these questions, and I will be discussing with you the solution for the same. And uh, when you solve these different aspects and you go for the clear understanding of this, you will be getting uh, some of the doubts meanwhile that you can uh, directly unmute and ask, or else what you can do, you can just uh, so in this lecture we will be going to solve these quizzes. These are some of the questions related to the week 2 content. And somebody is, can you Sadev, can you just make sure my screen is visible and I'm audible? Can you just make sure, like, I'm unable to get it, or else you can type it down in the comments or in the message box. So so in the filtration part, as far as the lecture content is concerned, you have been taught about uh, batch filtration and the continuous filtration modes. And in that, let me just come to the new section. Yes, yes. So this, there in the filtration, the solid liquid separation is happening. So filtration, this basically involved solid liquid separation. And here, this filtration may be defined as a solid liquid separation process carried out either under pressure or in the vacuum, resulting in the separation of the undissolved particulate suspended solids from a solid liquid mixture by passage of most of the fluid through a porous media that retains the solid on it. So sometimes we will be having different kind of porous media, like sometimes this directly this clothes and membranes are being used in order to carry out the separation via the porous media. So so this particular lecture will around will involve around these questions. So the first question that is there is, for toxic sludge, which type of filter media is used? So for toxic sludge, which type of filter media will be used? That is the question. And though there are different type of filter and there is different type of media, but which has to be used for toxic sludge is what? So there is like sand bed, cotton weaves, metal wire mesh, and satin weaves. So which one will be used for plastic sludge, toxic sludge? So how you will be going to talk about this is like these if sand beds are there, or like cotton weaves are nothing but the cotton created porous structures which will be there, metal weaves, satin weaves, and sand beds. So these are some different type of filters that will be installed inside. But when you go for the toxic sludge, so for the toxic sludge we usually prefer sand bed, because if the sludge is toxic, then it's if it the filter, the media that you are using, that should be easily cleanable. And if it has happens, then that particular filter media will be a good media, and that will be considered in any way in order to remove the toxic sludges. The at the end, when you are in the washing cycle, the toxicity should be removed through the media. That is the target. So the sand bed is the option that is the correct option for the given problem. And this 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 sand bed is the correct option for the given question. And then if you look at the another problem which is there is, uh, what is V in the ultimate filtration equation? So what is, first of all, what is ultimate filtration equation? What is the final filtration equation that you had? When you see that final filtration equation again through the slides also, it will be clear. You had this for the, there is two filtration, constant rate filtration and the constant pressure filtration. And for the constant pressure filtration, you had uh, dt by dv equals to mu divided by a pressure drop alpha v c divided by a plus rm. So here this alpha v c is the obvious area, and this v v is the superficial velocity, uh, and here this v is what? So this v is volume of the cake formed when 1 meter cube of the filtrate is collected. So volume of the cake formed per unit filtrate is collected. That is nothing but uh, the, the 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 volume of the cake, that is v in the ultimate filtration equation. So here second will be the C option will be the correct choice for the given problem. So let me come to here. Yes, C is the correct answer. And now if you look at the lecture portion also. There it's been discussed that uh, this this you have been had lots of types of the filtration, deep or deep bed filtration, and then cake filtration, depth or deep bed filtration, and in that you had some thorough discussion. Filter media requirement and why it is required. So filter media is basically required to retain solid to be filtered. That is the point number one. And then give a reasonable clear filter rate, does not plug or blind, be chemically and physically resistant to the process condition, and permit cake to be discharged cleanly and completely. So not be too expensive. So that cake to be discharged, and that toxicity effect should also be there. So in that sense, different filters are being used. Like here you see there is different satin weave. So what is satin weave? You see, uh, if you look at this carefully, uh, cotton weave, satin weave, twill weave, double layered weave. These are different kind of filters which are there. So woven material made up of cotton, wool, silk, nylon, polyesters, and glass fibers and metal wires are mostly commonly used as the filter media. Beds of the granular solids such as sand are also used in order to handle highly corrosive sludge is handled, and at the same time you can handle the toxic chemical. So this is for this, if you want to expand the answer to this is uh, uh, highly corrosive and toxic materials could be handled using this particular uh, filter. Now, coming to to a numerical problem that we will be going to solve, and then similar some of the problem I will be leaving in the lecture for you to solve, and we will see that how many questions we are going to get done at the end. So the question one says this: the volumetric flow rate during constant pressure filtration is the volumetric flow rate during constant pressure filtration is it is given by dV by dt. That is nothing but the volumetric flow rate uh, equals to 1 divided by Kc V plus 1 by Q0. Okay, where V is total volume of the filtrate collected, V is total volume of the filtrate collected in time t, in time t, and Kc and Q0 are constant. Kc and Q0 are constants. When when V equals to 1 liters and time equals to 4 1.3 seconds, and when v equals to 2 liter, time is equal to 108.3 seconds. Then the value of Kc is, then the value of Kc is, so the value of Kc you have been asked. So this is nothing but the compact form. So this is nothing but the main equation that you had, dt by dv. This equation that you had, uh, when you rearrange this equation, then the when you rearrange this equation, then you are going to get the equation of the form dv by dt, that is dv by dt, equals to 1 upon kct plus 1 by q0, kcv plus 1 by q0. So first of all, how this equation came, and then we will be going to take the data point that is given in the problem, so that we are actually in a situation to solve the problem. And this this will be a bit again recap of entire calculations that were there in the lecture, lecture number 7 and 8. And then this entire thing will be done. So the thing is, this dv by dt equals to 1 by kcv plus 1 by q dot, it is given in the problem. And when you actually calculate this, you just have to uh, this is the filtration equation, filtration equation. And when you actually rearrange it, you will be getting dv kcv plus 1 by q0, okay, equals to dt. That is the first step of the rearrangement. And then when you take this dv inside, then you will be getting kc vdv plus 1 by q0 dv equals to dt. Integrating both sides, integrating both sides, both sides, integrating both sides, we get, when you integrate both sides, you will be getting integral kc will be constant, so it will come out dv plus 1 by q0 is the constant as given in the question. This is given in the question, you see. uh, this kc and the q naughts are constant, so 1 by q naught will definitely be constant. dv equals to integral dt. And when you go a step ahead in this, so this will be kc, integration of vdv will be v square by 2 plus 1 by q0, integration of if dV is V equals to T. So when you rearrange it, you will be getting T by V equals to KCV divided by 2 plus 1 by Q0. And further, this could also be written as KCV square by 2 plus 1 by Q0 V equals to T. So in this, it is given that at V equals to 1 liter, uh, the here it is given that, see, it is given that to save time, okay, at V equals to 1 liter, time is 41.3 seconds, and at V equals to 2 liter, time is 108.3. And what is V? V is the total volume of the filter is collected. So total volume of the filter is collected is the V, and this is given to be what? This value is given. So when you substitute these values, so for V equals to 1, this equation Kc V square by 2 plus 1 by Q0 V equals to T. When you substitute, then you will be getting Kc 1 square by 2 plus 1 by Q0 into 1 equals to T. T is 41.3. And then another one is Kc 2 square by 2 plus 1 by Q0 2 equals to what? Equals to 108.3. And this uh, these both the values were given. So from here you solve for the value of Kc and the Q0. So this could be solved. So solving the first equation, we will be getting what? Kc by 2 plus 1 by Q naught equals to 41.3, and here 2 Kc plus 2 by Q0 equals to 108.3. So from here, substituting one of the value, so putting, this is equation 1, this is 2, put 1 by Q0 from equation 1 in equation 2. So when you do this, from equation 1, 1 by Q0 value will be 41.3 minus Kc by 2. And when you do this, so the second equation become, equation 2 becomes, this was from 1, 2 Kc plus 2, 41.3 minus Kc by 2 equals to 108.3. And this value will come out to be, value of Kc we have been asked to calculate. So this 2 Kc plus 6 to 8 plus minus Kc equals to 108.3. So this is Kc equals to 108.3 minus 82.6. So this comes out to be Kc equals to 25.7. This is seconds per meter 6. So this is the answer to the problem given. So this was based on the constant pressure filtration, and during the constant pressure filtration also the similar approach has been used. And this particular Kc and Q0, if you want to get somewhat more clarity about this in the second lecture, I mean, this has been clearly explained that. Let me just repeat it, like how that equation came up, whose solution gave the value of the Kc. And what is the Kc? What is the physical significance of the Kc? This, yes, it is here. So, this story begins with the resistance calculation for the each layer, and then that resistance calculation leads to the value of Kc, and then the constant part, which is 1 by q0. So, so this entire design equation for the batch reactor starts with the batch filtration. Starts with the pressure drop calculation. So this pressure drop has been calculated with this scheme. Suppose your slurry is flowing from this direction and this is the filter rate. So definitely there will be some resistance provided by the filter rate, but with the time what will be happening, some of the solid particles will be accumulating here at the very adjacent layer of the filter rate, and that will have again its own resistance, that is nothing but the cake resistance. So there will be two resistances involved. First is the resistance due to filter rate, second is the resistance due to because of the cake. And this pressure drop during the cake filtration will be calculated as delta P, which is PB minus PA. And further, this PB minus PA can be further separated in this fashion. So there will be two resistances. First is the pressure drop over cake. Second is the pressure drop over media. So these two resistances combined give the overall pressure drop. And this overall pressure drop uh, uh, will be there. And from the Kozni-Karbon's equation, if there will be cake formation, that cake will be having its some porosity, because that will be consisting of its this. Suppose this is the filtrate. So this is made up of something like some cloth. This is filtrate layer. This red one is the filtrate layer. Fil Filtrate layer, and the here, from here slurry is coming up, so there is a layer of this cake forming, and that cake will be providing its own resistance. So this resistance, because of this blue reason, that is because of the cake. So there will be cake. So this cake is what? This cake is porous bed. Okay, this forms porous bed over the filtrate media. Over the filtrate media, this porous bed is forming up, and so this whatever flow of the remaining slurry is happening through this media, it is analogous to what? Fluid flow through a packed bed or granular solid. So flow analogous to fluid flow through packed bed or granular solid. That is the most important point over here. And this this assumption clears the way to use the Cosney's equation. So if the particle in the cake are uniformly wetted by the filter rate, then the Cosney's equations can be used to compute the pressure drops, and hence using the Cosney equation, the pressure drop has been calculated, which says U dash, which is the superficial velocity, uh, which is velocity of the fluid through the bed, U dash, this will be equals to my pressure drop. This is the overall pressure drop in the cake plus K mu FL RH square, and RH is the hydrodynamic radii that will be calculated through different. So RH is the void volume to the total surface area of the particle, which can be calculated as epsilon divided by SD 1 minus S, where SD is the specific surface or surface area per unit time, per unit volume of the particle that are there through which the bed has been constructed, and the volume fraction of the bed is the epsilon, which is calculated by volume, void volume to the total volume. So when you put the value of the RH over there, you will be getting this. And this U dash is the one that will be used in subsequent part. So when you actually go for it, this is the superficial velocity. So this superficial velocity will be defined as the rate of uh, filtration per unit area. So this is meter cube uh, divided by second divided by area. This will be the nothing but the velocity. So in this way, this dv by dt is getting related to the pressure drop and the property of the fluid, which is viscosity. So definitely in the first slide we have learned that the filtration and its rate depends on the viscosity, temperature and all. So on temperature it only depends because the viscosity is the function of temperature over there. And then this, when you rearrange this, and the value of alpha depends on the void, and at the same time value of alpha depend on the sp value. Sp is what? Specific surface of the particle. So this sp value uh, along with the void fraction gives the value of the alpha, which is the specific cake resistance. And then you go for the final expression. So there will be two types of filter case. One is the compressible and incompressible. So about that the discussions are there. And then this final expression, when you go for it, it is giving up the the desired form that we were talking about. This in this, where you reduce this, so here your dt by dv is the same like in the problem it is given. In the problem it is given dt by dv. So this dt by dv is same. Here you see, when you rearrange it, you will be getting it. Here B is 1 by Q naught. So that's the rearrangement of the factors are there. So another question we will be going to solve now. And this question is again a numerical problem related to the filtration. And let's go for it. So this a constant pressure filtration test gives data that can be. So this will be involving the concept of leaf filters also, concept of compressibility. Uh, so so question number 2 says, I will be writing it down so that a constant pressure filtration test, a constant pressure filtration test gives data that can fit an that can fit an expression, and the expression is dt, and the expression is dt divided by dv equals to 9.3 v plus 8.5. Okay, where t is in seconds, and v is in liter. Okay. Another point is, if the resistance of filter media is assumed to be unaffected, and the compressibility coefficient of the filter cake is 0.3, the filter cake is 0.3. If the resistance of the filter media is assumed to be unaffected, means Rm is constant, and the compressibility coefficient of the filter cake is 0.3, and this information is given for the specific cake resistance, so that is 0.3. What will be the time taken? What will be what will be the time taken? What will be the time taken for the calculation, for the collection, for the collection of 3.5 liters of 3.5 liter of filtrate when the pressure used is twice that used in the test? When the pressure used is twice that of the filtrate, that of the test. Okay, so this question had three basic points, and you are asked here, what will be the time taken for the collection of the 55 liter of the final filtrate? So solving this is like, usually what happens, the value of the specific cake resistance alpha is the function of delta p and s, which is compressibility exponent of the cake, like compressibility coefficient sometimes we call it. So if I write it to tell you like this, alpha is what? Specific cake resistance. So this is a specific cake resistance. When you look at the equation here, uh, in the second term, you see this alpha is coming up, this alpha, and this alpha comes up because of the cake. One is because of the filtrate media Rm, and another one is because of the cake. So whatever cake is really getting accumulated over there. So this alpha is a specific cake resistance. So this alpha is the function of what? This alpha is function of delta P, and this alpha is function of a compressibility exponent of the K. So this is compressibility exponent or coefficient. I can tell you compressibility coefficient, compressibility coefficient, coefficient. So using the alpha equal to alpha 0 delta to p to the power s, when you see this expression, so this expression has been taught in the class also, and I will be going a bit one step ahead in this. uh, Let me take you to the concept where it has been taught. So this alpha value, here the different kind of expressions for the, so what are the filter cake? So filter cake are the cake which is formed, the layer which is forming, and that will be having anyway another resistance. So this incompressible is what? Alpha is independent of the pressure, so this function is will not be varied over there. So this expression here, delta p, will not be there. If for the incompressible, if your cake is incompressible, alpha is independent of the pressure drop, and uh, uh, and for the compressible cake, the alpha is dependent to the delta p. So compressible is what? Formed when the cake is not made up of individual rigid particles. So for the sand and everything, most of the time incompressible is the situation, but it is not the same for the compressible situation. And alpha varies with the distance from the media. Cake nearest to the surface of the media is subjected to the greatest compressive force and has lowest void. So this question I also I wanted to ask you. Uh, I will pose it later, but the thing is, like like if I tell you this part, after this question I will be asking that. So this expression for the alpha equals to alpha 0 delta p as delta p to the power s, and this confirms that this alpha is the function of the pressure drop, and the pressure drop will be anyway varying at the different layer location, and hence when the pressure drop will be varying, uh, there will be some changes into the situation. So this particular equation I am talking about, alpha equals to alpha 0 delta p to the power s. So it is the case of the compressible sludge, and there the compressibility factor comes up, coefficients comes up into the picture. And when you use this compressibility coefficients concept in order to get the insight of the calculation which is going on, then you will get that this delta s p to the power s, and if this s equals to 0, then this will be constant. So for the non-compressible case, for the non-compressible cake, and taking it as a linear function of delta p, so if s equals to 1 is for completely compressible pressible cake. This is the specific cake resistance, and this specific cake resistance, when you go for this, uh, this will be coming up in use in great sense, like the one here you had clarity about this. This alpha value will be, as in the problem, alpha value as value is given, then the compressibility has to consider. And when you are actually considering the compressibility factor into the play, then the say equation becomes a bit tedious in solution, but let's see. So here it is given that dt divided by dv equals to, you see, 9.3, 9.3 v plus 8.5, 9.3 volume plus 8.5. So when you try to solve it with the given conditions, then this uh, there is a method, different notational method that could also be used when considering the c value, and this yes, 9.3. So dt by dv 9.3, and the value of v is given over here, and you need to get uh, what will be the time taken for the collection of 35 liter of the final filter rate. Okay, so so when you will be considering the value of alpha as the function of s, then what will be the changes? So there will be changes in these coefficients coming up for the final expression, and through that you will be calculating. So how those changes will be made is like, let me first go to the main equation. Like you know that this dt by dv equals to mu divided by a delta p alpha v c divided by a plus mu rm divided by a delta p. I am writing it delta p. Sometimes it is written as minus delta p, but it is the pressure drop. So when you rearrange it, it is written as dt by dv equals to, this is what, this entire term when clubbed together, this will be acv plus this entire term is 1 by q0. This is for the constant filtration, constant pressure filtration, constant pressure filtration. Okay, so here the value of kc is what, where kc is equal to mu alpha c divided by, c is the concentration of the slurry initially, a square delta p. So here this kc is the function of alpha. Kc is the function of alpha, and now in the compressible case, this alpha is again the function of delta p. So this delta b delta p factor will be coming up into the calculation, and further this as consideration has to be done. So this entire equation which is there, dv dt by dv 9.3 v plus 8.5, this could also be expressed in another way in order to ease the calculation, is like d theta divided by dv equals to 2v by c plus 2vf by c. So I will be telling you this. Here theta is the filtration time, just the change in the unit, filtration time. Okay, and this v equals to volume of the filter rate, volume of the filter rate, filter rate, and this vf is what? Volume of the filtrate held in filter medium. Volume of the filtrate held in filter medium. So d theta by dv equals to 2v by c plus, this is what, time per unit volume, and again this is what, volume, and this is c. So when you go ahead, you see this c equals to, c is the factor whose value is c1 delta p divided by alpha. c1 delta p divided by alpha, where this alpha equals to, we know, alpha 0 delta p to the power s for compressible cake, and alpha equal to alpha 0 for incompressible cake. Okay, so in this way, this is the one, and this s is the compressibility factor, as we talked about. Compressibility coefficient or factor, coefficient, and alpha is the one that is specific cake resistance. So when the filter media is negligible, like here it is said, the resistance in the filter media is, if the resistance in the filter media is assumed to be unaffected, so if it is unaffected, the value will be constant, and in some case if it is negligible, then your second term will be vanished. Here only the first term will be there, 2v by c. So like in the first case, it was there, the situation was like in the first case. And when you use these expressions in order to get the solution for the problem, then uh, here dt by dv equals to 9.3v plus 8.5, and this d theta, so d theta by dv, let me write it, yes, d theta by dv equals to 2v by c plus 2vf by c. So this is 2v by c plus 2vf by c, and this when you write here, you know that here c equals to c1 delta p divided by alpha, and alpha equal to alpha 0 delta p to the power s. So here alpha 0 delta p to the power 0.3 as given in the problem, and this alpha 0 to the power 3, delta p to the power 3 thing will have its own uh, value, and when you go a bit ahead here, what will be the case? You just have to change the c here, like kp and kv you had here. You have to just look at the value of c, which will be anyway getting those constant. So this c equals to c1 delta p divided by alpha. So this is c1 delta p divided by alpha is what? Alpha is alpha 0 delta p to the power 0.3. So when you rearrange it, you will be getting c equals to c2, some other constant will come, c1 by alpha 0, and here it will come out to be delta p 0.7. and this delta p 0.7, delta p 0.7, uh, let me see some message came. Delta p 0.7 to the power 0.7, and this this is the changed value. So when you resubstitute it there, so like theta or t is the same, so let it write to be dt by dv equals to 2v divided by c2 delta p to the power 0.7 plus 2vf divided by c2 delta p to the power 0.7. This is the value of c1. Question 1. In the problem, it is given that the value in the problem, the question that you are given with is dv equals to 9.3v plus 8.5. So from here, when you compare it, you will get 2 by c2 delta p to the power 0.7 equals to 9.3, and this is the case 1. And the when the pressure used is twice, this is the one case, and when pressure used is twice, then what will be the condition? What will be the condition? 2 divided by C2. This will be the same, just this pressure drop will be double, 2.7. Then after calculating, this value will come out to be 15.107. Why? This 2 to the power 0.7 will adds up and 9.3 will be anyway same. So this 15.107 will be the value coming up for the increased pressure. Like in the question it is said. You see, here it is said that what will be the time taken for the collection of the 3.5 liter, 3.5 or 35, we have to see 3.5 liters of the filtrate when the pressure used is twice that of the initial test. So similarly, when you solve for the second term, so second is 2vf divided by c2 delta p to the power 0.7 is what? Is 8.5. Initial, this is initial, and finally what happened? This 2vf is same by c2. This became 2 times, and on calculation you will get it to be 13.81 when pressure becomes twice. So this became 13.81, and so the new equation, so new filtration rate equation will be, so both the constants are changed now. So dt by dv equals to 15.11 v plus 13.81. So see, this 13.81 is the second form and the 15.11 is the first. So this was the beginning, but finally after the increment of the pressure to be twice, this value came out to be this 15.11 v plus 13.8. Now the question is, you are asked to calculate the time for which the collection of the filter rate will be 3.5. So now the question is how you are going to solve it. You just rearrange it. dt equals to 15.11 v plus 13.81. This entire is dv. Integrate it from, you are asked 0 to t dt equals to 15.11 v plus 13.81 dV, and this integrated to 0 to 3.5 is the final collection of the filter rate that has been asked in the question. So when you solve this integration, I will be actually going for this 0.0 dt equals to this 15.11 into v square by 2 plus 13.81 v equals to 0.3.5, and when you calculate it, t equals to, from here, 15.11 over 2 multiplied by 3.5 whole square divided by 2 plus 13.81 into 3.5. So this comes out to be t equals to 140.87 seconds. So t is 140.87 seconds. So you see in the question, this filtration rate equation has been given initially, and it has been asked that the cake is the compressible with the compressibility coefficient to be 0.3, and the resistance in the filter media is assumed to be constant. So what will be the time taken for the collection of the this 3.5 liters of the filter rate when the filter rate is twice that of the test. So that's it for this particular question, and I hope you got something out of this. And let's solve another problem related to the filtration. So I will be solving it with the two method. One is the method that we had, this d theta by dv, like you are changing the terms into 2v by c. That is nothing but just way of expressing the same equation. So what happened? Yes. So this, the next equation, before that, just solve some of the small questions first. So yes, so the some of the small questions, then we will move for the good problem again. So this third is at optimum cycle time, the time for the filtration is, at optimum cycle time, the time for the filtration is, uh, the options are as follows. The options are as follows. Uh, First is equal to the difference of the time of the washing and time of for which the filter is out of use, equal to the difference of the time uh, for which the filter is out of use, and the time of washing equal to the time for which the filter is out of use. And as far as you remember, the optimum time calculation has been done, and there you got to know that this theta value, the optimum time for the filtration, is actually dependent on two things. One is that three, like many things. There is assembly, there is passing time, there is this some extra times in lodging, cleaning, and all. But the most important was the filtration time, and in that, when you looked at the filtration time, yes, this is the that and that. So here, V day will be this, how this is calculated. Let me tell you. Oh, so this is the filtration cycle. So filtration cycle is what? T filtration plus T was plus something extra, some other time. So TF is time required for the filtration, and T was is time required for the washing of the cake. And this is equal to the volume of the wash water per unit rate of the washing. uh, and TTC is time for the drilling, filling, opening, dumping the cake, and the reassembling it. So this T filtration, when you are assuming for the constant pressure and the incompressible sludge, filtered medium resistance is negligible, and thus when you consider that, then in that case this dt by dv equals to vp by v, kp by v, and there will not be constant term coming up because this will be this rm term will be zero. So only one term will be coming up, that will give the value of t filtration. So in that, there this t cycle has been calculated using t filtration plus t was plus t etc, and for the optimum cycle the value of this t was t cycle which was there, this t cycle used to calculate the daily output of the filter rate, and in order to maximize this daily output, this has been differentiated with respect to the filter rate. So when you differentiate it with the VF filter rate, so what will be the critical filter rate volume at which that V day is will be optimum or the maximum, that has been calculated, and you got this value. And from here, this has been assumed, or it has been conferred that the at the optimum cycle time, the time for filtration and the washing will be equal to the time for which the filter it is out of the use. So the optimum cycle time, the time for the filtration is equal to the difference of the time for which the filterate is out of use and time of washing. So which of the following is the correct one? You just look at this, uh, and uh, equal to the difference of the time for which the filterate is out of use and the time of washing. So here, uh, first one sand this, and another one was the C option, and the third one is B option. So correct answer for the question. And for the constant, another question is for the constant rate of rate and the compressible sludge, this S alpha 0 and Rm. So this, for the compressible alpha is alpha 0 delta P to the power S, and this constant rate for the constant rate, this and compressible is there, so this has to be calculated, these values has to be calculated, and Rm has to be calculated because nothing is set for this. This alpha 0 Rm and S all has to be calculated. So four option is the correct. Some other theoretical problem that you want to address here is this one, that says how cake is removed in a leaf filter. So let's take 11th question also. Which statement among the following is not correct for the vacuum filtration? First is clean filter rate is about to found due to vacuum. Another is the sample collection is difficult. Another is a disassembling is difficult in vacuum filtration. Less dry cake is obtained. How cake? So which of the following among the correct option? So the 11th question, when you look at this, the 11th question is actually, uh, when you see this, this is like This sample collection is difficult in the vacuum filtration. So that is there in the slide. Uh, so everything is well written over. So just clarity. So this will be like a reminder for you to look at this. Like which statement among the following is not correct for this. So, for the vacuum filtration, we know that clean filter rate is found due to vacuum, because vacuum helps in cleaning, and when you are washing, whatever is being washed, that are getting vacuumed outside, because you had this particular here, lots of vacuum juggleries were there. So if you want me to repeat that, so I will be going to the lecture slide where this has been well explained, that this no, it is here. Yes, it is here. So this these are the knobs where this vacuum is happening, vacuum filter. So these Y-shaped channels are there. They are the one washing is happening, and at the same time vacuum is happening, so that the entire clean sub it is again ready after the cake removal. So what is happening? Filling, cake formation, dewatering, washing, dewatering, and the cake removal is happening. So this is the one that has to be looked at. And the another is how cake is removed in the leaf filter. So the leaf filter, this was the last lecture. So in that, the you have been taught about, like these were the filters that you have been talked about. This batch pressure filter, in the batch pressure filter, and uh, there you got to know about plate and flame filter, and then pressure leaf filter, and the continuous pressure filter also was there, and there was the centrifugal filter that are having both the modes, batch and the continuous. And again, the two vacuum filters were there in the batch, in the continuous. In the batch, it was the vacuum leaf filter, and in the continuous, it was the disc filter and the rotary drum filter. So this entire filtration cycle was there, and you uh, question is how cake is removed in the leaf filter. So this here you see, here cake is there, so cake needs to be, vibration is happening, so these vibrates in order to get the cake out, and from here the cakes are getting out. So this use of vibration is done in order to do the cake removal. Knife is used in press and frame filter, leaf filter, disc filter. Which of the following is correct? So when you see this, this is the basically knife which continuously removes the cake. So where is that knife? At the verse, it is there. So disc filters will be there. So you see, this is this filter. Here something is there in order to cut that. So the answer to this is disc filter will be having the knife. And then in the similar way, other two questions are there. You see the question number 14, which says, which says uh, uh, thick, thin cake is formed in which thin cake is formed? Drum filter, plate and frame filter, leaf filter. So where in everyone there will be cake formation, but in which one there will be the thin cake formation? So in the drum filter, basically this thin cake forms up. So these are direct theoretical questions that has been taken from the slides. And another one is infiltration. Alpha accounts to the resistance of the total cake, resistance of the initial cake of both of the above, none of the above. So, so this is specific cake resistance. So this accounts for the total resistance of the cake. So in this way, and the in the continuous filtration, constant pressure is followed by the constant rate. Constant rate is followed by the constant pressure, and constant rate occurs with the constant pressure. So what happens? So if you remember the very first lecture of the filtration, there has been one plot that was talking about this this I mean this pressure uh, and the dt by degree rate, and there was where you came to know that the curve, this one, this says that constant rate and the pressure filtration. So as continuously cake is there and cake is forming up, cake thickness is increasing, cake is becoming more and more compact, and its porosity is decreasing. So there is need that initially you operate the filtration unit at the flow rate which is constant, and later you operate it at the pressure which is constant. So initially increased flow rate, constant flow rate with the gradual reduction in the flow rate when the pressure is being kept constant will be the optimum situation for its operation. So when you see this in continuous filtration, constant rate is followed by the constant pressure. Constant pressure is followed by the constant rate. So the option A is correct answer for the question number 9. So constant rate occurs with constant pressure. Oh, no, both occurs with constant pressure. There will be nothing followed. For continuous, you want continuously, so both are occurring. This is true for batch one, but the constant continuous one both occur simultaneously. So somewhere it is also explained that when you are going for the continuous filtration, like in the case of the centrifuge, some of the equation has been explained. There, it has been taught that this all the equation of the batch reactor, batch filtration unit is applicable to the filtration unit for the continuous. But as in the batch, there was the constant rate and the constant pressure kind of thing. But in the continuous, there is nothing like that. It has to be operated at constant rate, occurs with the constant rate. So both things occur simultaneously, and this is explained here. And this see, oh, it's almost there. Let me reach there. Mm, yes, it is it. So thus, the equation developed for the batch filtration can be used for the continuous filtration as well, keeping in mind that the equation stands for one for full one rotation. So one rotation will be one thing, and this in the continuous both occurs. Yeah, and then this was the discussion like how this happens. This is the continuous filtration unit, and these are the various flows diagram that are there, like slurry is going, slurry is coming up, rotary drum is there, there will be washing system, solid collection is happening here, cutting is there. Only 20% of the of the area will be dipped. So that is the next question that I am talking about. During continuous filtration, if 25% of the area of the drum is collected with the slurry, then value of F should be. So if contact with the slurry, so if 20% is in the slurry, you see, this is the drum, this was the slurry, this was the slurry, and here, if 20% is in 0.2%, no, 20% is in this case it is 25% is in contact with this, then the fraction will be, this F will be what? This F will be 0.25, and this F is here. It is well explained in the lecture. When you see this F, you will come to know that this no, not this F value yes, so this F value is calculated. This is the fraction of the part which is dipped up, which is inside. So if you want me to explain it again, this is the factor F that I am talking about. Here you see where this F is the fraction of the cycle available for the cake formation. So there will the entire cycle will be there, and some part of the cycle at the bottom is available for the cake formation, and then further somewhere it is washing is happening, somewhere the cutting is happening, and in turn thing is under the vacuum. So vacuum is sucking it up in order to maintain the clarity of the filter rate. So 0.25 is the correct answer. That is the fraction. And let me solve another question. These questions are similar problems that I am solving over here. The similar problem has been solved in the lecture also. So these I am leaving for you, these two, and maybe I will solve one of them. And this one this one is the very straightforward problem. In this one, your this is anyway rotary one, and you see this rotary one. I will be explaining a bit. Here you see this says a rotary filter operates at the 0.04 hertz. Filters at the rate of the 0.0065 meter cube per second, operating under the under the filter close. At what speed must the filter be operated to give a filtration rate of 0. To give the filtration rate of 0.02? It has been asked. Like in the beginning, it is giving a filtration rate of 0.0065. So initially the filtration rate is V by T is 0.0065. It is 1. Finally, it is asked that when it will give this 2 meter cube per second. Then what will be the operating under what speed? So speed that is in terms of frequency here it is said. So like in the lecture, it is clearly shown that from here you see this time for the continuous filtration, that is nothing but the rotary one. You see this is the rotary one, this is the continuous filtration unit. See that the rotary drum filter, this is the continuous filtration unit, and here this time is directly proportional to square of the volume of the filter rate. So time is directly proportional to the square of the volume of the filter rate when there is no cake resistance. So we have to assume that anyway in order to get something out of this. So this you see here it is directly proportional to the volume of to the square. And when you look at the problem, this shows that shows that it is v square is directly proportional to time, and time is inversely proportional to the frequency. So from here you can calculate that v is directly proportional to n to the power minus 0.5, and t is directly proportional to n to the power minus 1. So v by t is directly proportional to what? If you go for this, then it comes out to be n to the power 0.5. That's what I understand out of this. N to the power 0.5, it depends. N to the power 0.5 means root of n. V by t 1 divided by v by t 2 is equals to n 1 by n2 to the power 0.5. Substituting the values here, you are 0.0065 divided by 0.02. This equals to n1 value, what is the value of n1? 0.04 hertz divided by this is you are asked to calculate, and this is 0.5. And when you solve it for n2, you will be getting 0.379 hertz to be answered. Okay, so that is the correct answer. 0.0379. 0.0379 is the correct answer for this. So in this way, this rotary and continuous filtration question will be solved. And now I will be taking you to one more good question, that is again related to the filtration, and I will be solving it with the two method. The one that I have already talked about, and the the one which is d theta by dv equals to 2v by c plus 2v by c express kind of expression. No problem. So that it clears up the another problem also if somewhere you stuck in that, because that compressibility factor involving problem usually is a bit difficult. So question says the basic filtration equation is given. The basic filtration equation is given as dt divided by dv plus mu a delta p alpha cv divided by a plus rm. This is the filter rate resistance, and here this is rm. Here you see next line says v is the volume of filtrate, alpha is specific cake resistance, then a is filtrate area, and mu is viscosity of fluid, mu is viscosity of fluid. So in a 20-minute constant rate filtration 5 meter cube filtrate was obtained. Okay, if this followed by constant pressure filtration, if this followed by constant pressure filtration, if this followed by constant pressure filtration, how much time in minutes will take which another 5 meter cube filtrate which another with another this has to be with another 5 meter cube filtrate neglect filter resistance neglect filter medium resistance filter medium resistance means Rm equals to 0 and it is incompressible. It is incompressible means there is nothing like alpha value. Alpha is not a function of alpha is not the function of pressure drop. So solve it. So solving it with the method 1. Method 1. Here, like you are having dt by dv equals to mu upon a delta p alpha cv divided by a. Okay, as Rm equals to 0. Now it is clear that another term becomes 0. So only this first term is there, Rm becomes 0. So for constant rate filtration t equals to mu alpha c divided by a square delta p v square. Okay, means here it is said that 20 minutes constant rate filtration gave them 5 meter cube of the content. So from here mu alpha c by a square delta p is calculated to be 20 by 25. Okay, so in constant pressure filtration in constant pressure, first was the constant rate you use for calculation of the value which is mu alpha c upon a square delta p. So here what will happen, here your this dt which is 0 to t mu alpha c divided by a square delta p equal 0 to v dp because this is constant pressure. So pressure is constant, so you took it out in this one. and you kept dt dv. So this has been calculated in a way like dt equals to mu alpha c upon a square delta v dv, and then integration is being performed here. Okay, it came from the first equation only. So this is like 0 to t dt equals to mu alpha c is 20 by 25, and here it is 0 to 5 for the next 5 vdv. So this will be 20 by 25t into v square by 2, 0 to 5, and when you solve it you are going to get t equals to 20 by 25, 25 by 25 by 2, this will be 10 minutes. This is the first approach that could be used. And the second method is method 2. It is similar, just the notation will be like that. So d theta by dv equals to 2v by c, the way I told you, plus 2vf by c. Here it will be 0 as there is no intermediate resistance provided. So for constant rate filtration, theta by v equals to 2v by c, theta equals to 2v square by c, implies 20 equals to 2 by c into 5 square, implies c equals to 2 into 25 by 20. Okay, and then this another is the in constant pressure filtration. What is the situation here? You will be having 0 to t d theta equals to 2 by c integral 0 to 5 vdv. So from here t comes out to be 2 divided by 2 into 25 by 20. Just the way of writing is different in this method, but it helps. So t equals to 20 divided by 25 into 25 divided by 2. So this comes out to be 10 minutes. This is the answer. So from both the method you got the same answer. And now let us look at the problem of this one, which is here. This says in a filtration the initial period is carried out at the constant rate, while with the feed pump at the full capacity and then the constant pressure. Okay, so like this diagram, first it is run at constant rate, then gradually rate is decreasing, and then it is run at the constant pressure. Okay, so the pressure is then maintained at the value for the rest of the filtration. The constant rate operation requires 850 seconds, and 1/3 of the time is obtained during this period. Okay, so this, how you will be going to get it like this. Yes, the pressure is then maintained at this value for rest of the filtration. the constant rate operation requires 850 seconds, and one third of the total filter rate is obtained in this period. Neglecting the resistance of the filter medium, compute the filter rate cycle with the existing pump for the maximum daily capacity. If now you knew that during that your for the maximum daily capacity, what are the things has to be considered? That has to have this equal to the difference of the time for which the filter is out of the use and the time of the washing. So that concept will be used here. So again this will be solved in a way like this. Let me just show you. Yes, here. Use this one. So here this 1100 is like total time, means the this time minus t1. T1 is what? The 850, which is required for what? Which is required for the filtration to happen. So if you see this, the 850 is what? The constant rate operation require 850 seconds. So 850 is the time for the constant rate. So if you calculate this constant rate time, this rest time can be calculated as t minus tt, and here it is said that that value is what? 1100. You see, compute the filtration cycle with the existing pump for the maximum daily capacity if the time for removing the filtrate and the assembly the press is 1100. So rest time is 1100, means t minus t1 is the rest of the time. So 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 for the optimum and for the maximum, like here said, for the maximum, for the maximum yes, for the maximum daily capacity, uh, uh, what has to be condition? Like if you calculate this td plus t1 as same as the filtration time plus the time required for rest of the things, that is 1100 is for rest of the thing, and for the filtration which is 1950. So now 1950 seconds is the one for, but for the total cycle of the time, this that is the like 2 etc. Rest of the time, this washing time plus filtered time becomes the time in which the filtration is not happening. So that need to be again added in order to get 3050. So 3050 is the correct answer here. So I will be just showing you up its concept in the slides so that it becomes easy. So in the slide you see this was here where the filtration time concept has been taught. Filtration time concept has been taught, and there they have clearly, yes, here you see this was the optimum time calculation. Here I think they have calculated it. So this is mm, these are very straightforward problem. Yes, here you see 2 etc. So the point is like we have total optimum cycle time is this. So this etc, whether this became the extra time 2 etc. So here we have optimum cycle time is 2 etc. So in this way we can define that the filtration cycle, and we optimize the cycle time so that all the theory part of now onward, so that can be discussed here. So this tf plus t was becomes t etc for the optimum performance uh, of the system. So this particular slide made this particular question. From here, the question has been created. For the optimum cycle time, the time for the filtration and the washing will be equal to that of the time for which the filtrate is out of the use. So that got added up. So that got added up. So here the total cycle time was time for the filtration plus time other time that has to be considered, which is TD. That is also given for the for what for reassembling and removing the cake, and then removing the cake reassembly, this was the time, and then the rest time, that was the TETC, was the 1100 that got up here. So 30 50 3050 becomes the answer for the question. So now this question is clear to you, and I just want to see, yes, 15 minutes is still there. So I will be looking at this particular problem which is there. So time is there, so we will be solving it. A plate and frame filter having 1.2 meter square surface area is operated at 2 bar gauge pressure and forms incompressible cake. So cake is incompressible, so though there is no nothing pressure dependence of the compressibility. Feed consists of the 8% of the solid whose specific gravity is 2.3, means 2300 is the gravity density. Viscosity of the liquid is 0.003 kg per meter second. Compute the washing time required to wash the cake formed at the end of the 100 minute of the filtering at the same pressure using 4 meter cube of the water. The operating data are, so you are given with the operating data, and you are given with the plate and frame filter which is having 1.2, so area is given. So if you take this question that side, let me see. Yes, another question is also related to this, so we will be solving both. So yeah, so this, when you solve, you will be you are giving with that time versus this filtrate volume plot. So V versus time you are giving with. So slope of the V versus time will give you dV by dt or dt by dV, whatsoever you are willing to calculate. So let's go for the problem itself. So yes, this is the problem. You see, this given data is A equals to 1.2 meter square, and this delta P is 2 bar. So this viscosity is also given over here. So viscosity is given, this density is given, pressure is difference is given, gauge is given, gauge pressure, and then area is given. So time versus volume, you are given with, converted that time to the second, because everything will be calculated per second, as the viscosity unit is also every second, so as I unit it has been calculated. This here you see this uh, this is like, from here they have calculated the difference in order to get delta T versus delta V data, and when you go for that, then From here you will get delta T by delta V calculated here, dividing this two, and using Excel this can be plotted easily. This is the linear fit of that. So from here you got to know that dt by dv that I was talking about came out to be this dt by dv, this dt by dv. Let me just put it a bit smaller. Yes, dt by dv equals to kp v plus b or 1 by q naught sometimes, and this is 37.27 v plus 41.49 from the graph reading you got it. And when you solve it or integrate it, taking dv this size, so this will be 37.2 v 27 v plus 41.49 dv equals to dt. Integrating you will be getting 18.635 v square plus 41.9 v equals to t. From here it is given that compute the washing time required to wash the cake formed at the 100 second. 100 minute means 6000 seconds. Filtering the same pressure using the 4 meter cube of the wash water using operating line. Okay, so using the operating data. So this at t equals to 100 minute means 6000 second. You see this VF is what? You just calculate using this quadratic equation. You will be getting 16.865 meter cube. This is the volume of volume. So the rate will be what? dv by dt. There will be 37.27 vf plus 41.49. You are having the value of vf, so you will get 0.00149 meter cube per second. So time required for wash the cake will be what? Wash the cake will be what? T wash equals to what? You just calculate it. And when you solve it, you will be getting 44.74 minutes. So the 44.74 minutes are the correct answer, which is 44.74 minutes are the correct answer. And in the similar way, from the intercept, when you plotted the graph, from here the intercept will give you the another value which is mu f rm by a delta p. So from here the area delta p and the mu f is given, so rm can be calculated. So if you see b equals to mu f rm divided by a minus delta p. So this is given, this is given, this is given. Intercept of what? dt by dv versus v graph. In this graph I am talking about dt by dv versus v graph. dt by dv versus v graph. And when you see this, the value of rm comes out to be, the value of rm comes out to be, why yes, the value of rm comes out to be 33.19 into 10 to the power 8. So rm equals to 33.19 into 10 to the power 8 meter inverse. The unit of rm is meter inverse, and this will be more clear when you actually plot this data uh, using graph paper or on the Excel sheet. So that is all. And rest, like a similar problem maybe in this week, you are given with maybe the 7th of the Fab is the date for the submission, I think. So you attempt them and you re-watch the lectures and the sums that has been performed by the instructor, combining whatever we talked today. And this small questions will be there anyway in the end exam also, finally, which will be there for the certification. And some of the mathematical and conceptual questions will be there, which will not be very lengthy, but at the same time that involve thorough understanding of the problem. So that's all for today. I think this is 5. And let me see. Yes, still. So that's all for today. Thank you. Any question? Maybe Meta is there or not? So on the chat also nothing is there. So let us meet in the next week. In the next week, the topic is fluidization. So next week lecture is fluidization and then the flotation. So the course was structured in a way covering 4 major pillars uh, of the mechanical operation. That was there. Like first was sedimentation. First week is sedimentation. Second week is filtration. Third is fluidization, and last one is flotation. So, so this 2 week is completed. So rewatch those lectures wherever you are facing some difficulty, and you can raise your concern in the portal also. Let me. I will be showing you in a minute, and then there will be fluidization in the 3rd week, and 4th week will be the fluidization. So you can raise your questions there at the Swayam portal. So this Swayam portal, if you go Swayam NPTEL portal, then there it is clearly, net is a bit slow. Yes, here the coursework is showing. Maybe another link. Yes, this one. Yes, here you see when you go for the course, toward the course, this recordings will be there, and at the same time you can raise your questions in the community. So ask question section is there, and that will be very beneficial in clearing your doubts. So the concerned person will be addressing your question. So here ask a question is there. So here you can ask question, and then somebody already asked some question, you see. Maybe if we can, you can see this. Yes. What is flotation? Flocculation. I have a question. What is happening in this video at this? What flocculation? Why? Flocculation is the process of aggregation. In this way, the instructors are uh, uh, giving you answers. And then there is some other question. What is particulate matter? So particulate matter term is general. On that denote both tiny solid and the fluid particle. Here we refer them in both the liquid and the gas. More about this topic comes in the coming lecture: filtration, sedimentation, and fluidization. So this way you will be getting your doubts done. And yes, that's all for today's lecture, and hope you enjoyed it. Thank you so much. Very blessed students are coming up. Thank you, Sadev. Thank you so much for being connected, and you solved the questions, and definitely there will be some clarity. Thank you. I will be stopping.